So for number 52, we're going to use the conservation of energy to determine the angular speed of the spool, shown in the figure after the 3 kilogram bucket has fallen 4 meters, starting from rest. The light string is attached to the bucket, is wrapped around the spool, and does not slip as it unwinds. Turns out energy is a little faster way of solving some of these problems, if you know the exact distance. Energy is always a sort of fast way of doing it. And what do we have in this case? Well, you can remember initial energy plus work equals final energy. And the type of energy we're dealing with here is the bucket's initial gravitational potential energy. In the end, our bucket's going to be moving, so it's going to have some kinetic energy. And our reel is going to be rotating, or a spool, and so it's going to end up with rotational kinetic energy. So all of the change in GP of the bucket falling is going to be converted into these two quantities. So we've got a height change here of 4 meters. And so we can actually solve this. Excuse me as I try to write 4 meters. So plugging in what we know. Change in gravitational potential, it's only the bucket that's actually falling. The spool is staying in place. Is going to equal 1/2 mv squared, where m is the mass of our bucket, plus 1/2 I omega squared, where I is the rotational inertia of the spool. And since we're only looking for angular velocity or angular speed, I'm going to get rid of velocity. Remember that omega r is equal to v, and what I'm going to do is substitute in this for velocity in the kinetic energy equation. That way I only have just one variable I'm solving for. So replacing v with omega r gives us this. And then to be able to solve this, I need to figure out the rotational inertia of the system. For the spool, 1/2 times its mass times its radius squared gives us 0.9. We can then plug that into the equation over here for I. So I is 0.9. And now we can solve the rest of this. Just doing some numeric calculations, we get these. We can reduce it down to here. Adding both the omega squared terms together gives us that. And then dividing both sides by 0.99 and taking the square root gives us approximately 11 radians per second, which is the final angular velocity of the spool.